And what if we don't have a uniformly distributed signal? So before we calculated the signal to noise ratio for a uniformly distributed signal, but as we saw, speech and audio signals are best modeled by a Laplacian distribution or a Gaussian mixed module, and even when we look at the sine wave, it doesn't have a uniform distribution. So in this next example, we are going to calculate the signal to noise ratio for a sine wave. Observe that if a sinusoid represents a full range signal, its values are from minus a divided by 2 to plus a divided by 2, as in the previous cases. The first step, what we need to do is to calculate the PDF of a sine wave. So what is the PDF of a sine wave? So basically it is the normalized histogram such that its integral becomes 1 to obtain a probability distribution. So here is the PDF of a sine wave. So it's given by this formula, and this results from the derivative of the inverse sine function. So we are going to use the PDF of time series to calculate this PDF of a sine wave and reach this result here. So given a signal A is equal to a function of t, which is sampled uniformly over a time period t, its PDF PA can be calculated as follows. Because the signal is uniformly sampled, we have P of t is equal to 1 over time period t. The function f of t acts to transform this density from 1 over t to 1 over a. Hence, using the method for transforming PDFs, we get P of A is equal to P of t divided by the absolute value of the derivative of dA in relation to dt, evaluated at t is equal to the inverse function of x. So we are going to use SimPy to calculate the PDF of a sine wave. So first I'm importing here all the functions from SimPy, and I'm defining the symbols I'm going to use, and here I'm defining the first equation will be x is equal to sine of t. Then I am finding the inverse, so it's this t is equal to the inverse of x. So here I'm finding the inverse, and I have that the t is equal to the arc sine of x, so it's the inverse sine of x. So the inverse sine is only defined for minus pi divided by 2 to pi divided by 2, and its PDF is uniform within this, hence P of t is 1 over pi. So here I am calculating the P of t, so this is to achieve this result, so we know it's uniformly distributed from minus pi divided by 2 to pi divided by 2, and when I calculate this PDF, we have that's 1 over p for minus pi divided by 2 to pi divided by 2. So this is the same what we calculated before for our quantization error for a uniformly distributed signal. So in a uniform distribution, and we have this 1 over this full range. So now we have already the P of t, and now we need to calculate dA of dt. So in our case, x is equal to sine of t, so we will find dx of dt, and we will evaluate at t equals to the inverse of x, so t equals to the arc sine of x. So this is what we are doing here. So this is the derivative, and then I am evaluating at t equals to the arc sine, and here is the result. So we have this part here. So now to calculate the PDF of the sine wave, we have this pt, we have this, we can divide one by another, and we have the final result, which is 1 divided by pi square root of 1 minus x squared, which is the same result that we've given here before.